In the last section, we took a look at the idea of approaching values, secant lines, tangent lines, etc. Another interesting concept is, let's take a look at a function. And let's just define the function as e to the x minus 1 over, let's say, 2x or something like that. Now, we know that the domain of this function, we know that x cannot be equal to 0. All right. If clearly that happens, then we're going to divide by 0. So we should expect some sort of asymptotic behavior around 0. So what's the behavior at x equals 0? Well, we might expect like asymptote, or maybe like some sort of gap, okay, or just some weird stuff going on. Let's take a look at what the graph actually looks like. So we're going to go into our calculator, and we're going to get y equals, and we'll clear this out. And I'm going to graph e to the x, so second e to the x minus 1 divided by quantity 2x. And I'm going to zoom standard. Excuse me. And I'm going to zoom in just a little bit. Now notice that there is no asymptotic behavior around 0. In fact, it looks like it's a pretty normal function. If I was to go zoom standard again, it looks like just a regular old e to the x function. So why is that? Well, it's the idea that sometimes a function is not necessarily defined, but it looks like it's normal. All right. Now, clearly, we can't plug 0 back into the function. So we go in here. So x cannot be equal to 0, since f at 0 does not exist. But if I was to trace the function, let's go back to the calculator. I'm going to zoom in again. Excuse me. And let's say I was to trace the function from the left, or from the right side, excuse me. And notice that as x gets closer to 0, it looks like y is approaching 0.5, at least from the right side. And if I put it right at 0, it doesn't equal anything. From the left side, it looks like that as I approach from the left side of the graph, it looks like as x is getting really close to 0 again, that y is getting pretty close to a half. And so we can suspect that by looking at the graph, it's kind of approaching a half, but we're not necessarily sure of that. So what's that idea? X can't be equal to 0, but the graph says x is approaching, or says that y is approaching 0.5 as x approaches 0. All right? So what is that idea? Well, that's the idea of a limit. A limit is a value that a function approaches but may not be in the domain of the function. So it is a value that a function approaches and the value of x may or may not be in the domain of the function. All right, so that's an important concept. In fact, a limit is one of the most fundamental concepts in all of calculus. All right, so we're going to be studying a lot about limits. In fact, the rest of this chapter 2 is all limits. All right. Now, before we get to any sort of problems with my math lab, I want to explain the idea of left-handed limit and a right-handed limit. So a right-hand limit is when the graph approaches from the right side. So a limit notation is this. So we say limit as x approaches some value a of f of x. All right, so that's what the limit notation is. All right. If you see this, lim as x approaches a plus of f of x, that means what's happening as x approaches the value a from the right side of the graph. Now, left-handed limit. That's the lim as x approaches a from the left-hand side of the graph. Right? And so when we talk about the left-hand and the right-hand limit, if we just have like a function that looks something like this, like we did before, this is lim as x approaches 0 from the right side. And this is the lim as x approaches 0 from the left side of the function. All right. Now we know that it doesn't exist at 0, but we know that as it approaches 0, it looks like the y value is getting to a half. So that's really what's happening with these limits. It's just numbers that we're approaching, but we can't necessarily say if it reaches or not reaches. One important concept of limits is that a limit exists if the left-hand and right-hand limits are the same. Okay, so if lim as x approaches a from the right of some function f is equal to lim as x approaches a from the left of f of x, okay, and that's equal to some value L, where L is a real number. What that means is that the limit as x approaches a of f of x is also equal to L, right? And if they don't equal, that means that the limit does not exist. Okay, so using all these concepts of limits, let's go ahead and take a look at a few basic examples where we can just analyze a graph and see whether or not we can determine limits. All right, so let's just take a look at a really basic graph here. So in the graph, we're given, this is just a function of h of x, and we want to find 5 different values. Okay, so we want to find h at 4, lim of h at x as x approaches 4, and then a few other ones. All right, so let's start with this one. All right, whenever you see this, what you're really looking for is you're looking for the solid dot. It's not a limit, it's just a function evaluated at 4. So you're looking for a solid dot when x is equal to 4. And that's going to be right here at the value 8. Okay, so we can clearly see that it lines up to 8. So for part A, the function h at 4 is going to be equal to 8, because there's a solid dot there. Now, what is the limit as x approaches 4 of that h? So lim as x approaches 4 of h at x. So what we're going to do is we're going to trace it from the left side. And again, we're just trying to zero in on 4, like what's happening right here. And it looks like from both directions, it looks like that we're lining up with 6. And so because it's approaching from both the left and the right side 6, that means that the function's value at 4 is going to be 6. All right. Now, that doesn't necessarily mean this always has an answer. Right? So another example, part C. We have h at 7, and we look at 7, and there's no solid dot. So since there's no solid dot there, what we like to say is that either DNE, and in mathematics when we see DNE, that just means does not exist. Okay. All right. Lim as x approaches 7. So we're going to trace from the left side, and we're going to trace from the right side. And notice what we're trying to do is we're trying to line it up at 7, and it looks really nicely that it's going to be equal to 3. So the limit exists even though the function does not exist, which is actually indicative of the very first example we looked at. So lim as x approaches 7 of h at x is going to be equal to 3. And probably the easiest one is going to be the last one. What happens as x approaches 8? Well, that's clearly in the domain of the function, so all we have to do is just trace it, and it looks like it's lining up really nicely to 4. and it does exist in there, so we don't even have to worry about that one. Nice and easy. So lim as x approaches 8 of h at x is going to be equal to 4. All right, so all we're doing is we're just reading the graph, seeing if the function exists or if the limit exists. Okay. Now, just one last example. Let's say we have another graph. All right, this one's a little bit different, obviously, and we're really focused on the value as to what happens at 2. All right, so in the last example, we were at 4 and 7 and 8, but this time we're just focusing right here at 2. All right, so we don't have to do too much work. So what is the limit as x approaches 2 from the left side? So what we're going to do is we're going to trace from the left, and it looks like that we're lining up to 4 from the left side. All right, so that's easy. It's going to be equal to 4. And again, it's from the left side because notice that we have this 2 minus. All right, so again, that just means we're going from the left side. Now we have 2 plus. So that means we're approaching from the right side. So we're going to look at the right of the graph. We're going to keep tracing it from the right. And again, we're going to line it up. All right, and it looks like this time it's going to be equal to 3. Now, clearly, what we notice is that 4 and 3 are completely different. So we're approaching 2 from different directions, getting 2 different numbers. So what can we say about the limit as x approaches 2? We say it does not exist because it's 2 different numbers from the left and the right. Finally, what is the value of f at 2? Well, we just look for the solid dot, and it lines up to 4. Okay, so f at 2 is going to be equal to 4. So hopefully this makes sense as to how we're going to go through and to be able to work with these very basic sorts of graphs that work with limits and how to identify a limit, definition of a limit, etc.